Have you ever looked up at the night sky? I mean, really looked. Past the city lights, past the passing aeroplanes, and into that deep, dark, velvet blackness. It's sprinkled with countless stars, isn't it? Each one a distant sun, perhaps with its own family of planets. It's easy to feel small when you do that, but it's also easy to feel a sense of wonder. What is all this stuff? Where did it come from? And a question that might sound a bit strange at first, what shape is it all? When we talk about the shape of the universe, we're not asking if it looks like a giant star or a cube. It's something much more profound. We are talking about its geometry. Now, you might remember geometry from school, things like triangles, circles, and parallel lines on a flat piece of paper. That's called Euclidean geometry, and it works perfectly for building a house or navigating a city. But what if the paper itself, the very fabric of space, wasn't flat? What if it was curved? This is the core idea behind the geometry of the universe. Imagine you're an ant living on the surface of a giant, perfectly smooth balloon. To you, your world might seem completely flat. Albert Einstein's theory of general relativity told us something amazing over a century ago. He showed that gravity isn't a mysterious force pulling things together. Instead, it's a consequence of mass and energy warping or curving the fabric of space-time. Scientists have narrowed it down to three fundamental geometries. The first is a closed universe, which is like the surface of that balloon we talked about. If you travel in a straight line for long enough in a closed universe, you would eventually end up right back where you started. It would be the ultimate round-the-world trip, but on a cosmic scale. The second possibility is an open universe. Its geometry is often compared to a saddle or a Pringles chip, but in 3 dimensions. This kind of universe is infinite. It stretches on forever in all directions, and you would never return to your starting point. The third option is a flat universe. This is the geometry we are most familiar with from our everyday lives. In a flat universe, parallel lines remain perfectly parallel forever, and the angles of a giant cosmic triangle would add up to exactly 180 degrees. So how do we actually measure the shape of something as vast as the entire universe, especially when we are stuck inside it? It seems like an impossible task, but scientists have an incredibly clever trick up their sleeves. They look at the oldest light in the cosmos. This light is an echo of the Big Bang itself, a faint glow that fills all of space. It's called the cosmic microwave background, or CMB for short. By studying how this ancient light has traveled through space for billions of years, they can deduce the shape of the room it has been traveling through, the universe itself. It's essentially a way of drawing the biggest triangle imaginable. The 3 points are us, the observer, and 2 edges of one of those ancient hotspots in the cosmic microwave background. In a flat universe, the light travels in a straight line, and the spots appear exactly the size we expect. If space is curved, it acts like a cosmic lens, making spots appear larger or smaller than expected. All the evidence we have gathered, most notably from WMAP and the Planck satellite, points overwhelmingly towards a flat universe. The spots appear to be the correct size. The universe isn't just made of one thing. It's a cosmic mixture of 3 main ingredients: regular matter, dark matter, and the mysterious dark energy. About 6 billion years ago, a major cosmic transition occurred. The universe had expanded so much that dark energy became the dominant component. From this point on, the expansion stopped slowing down and began to accelerate. This discovery was so shocking that it earned the scientists who found it the Nobel Prize. So what exactly is this dark energy that now dominates the cosmic landscape? The honest answer is that we don't really know. What we do know is that it acts like a pressure that's inherent to the vacuum of space itself. Unlike matter, whose density gets diluted as the universe expands, the density of dark energy appears to remain constant. As space gets bigger, more dark energy comes into existence. So could this dramatic takeover by dark energy actually change the shape of the universe? Could a universe that we measure as flat today become curved in the future? In the simplest model, dark energy is a cosmological constant. If this is true, then the universe's geometry is likely fixed for good. However, some theories propose a dynamic form of dark energy that could change over time, opening up all possibilities. We have this epic tug-of-war playing out across the entire universe. Gravity constantly trying to slow expansion and make things clump together, while dark energy works to speed expansion up and drive everything apart. The geometry of the universe is intimately linked to the outcome of this struggle. The balance between these competing influences dictates the final curvature and ultimate fate. Our very best measurements tell a remarkably consistent story. They reveal that our universe has a geometry that is indistinguishably flat, an infinite expanse without boundary or edge. This flatness implies a very specific cosmic recipe. About 5% ordinary matter, 27% dark matter, and 68% dark energy. Our understanding is perhaps most defined by the vastness of what we still do not know. The biggest mystery is the nature of dark energy itself. A new generation of powerful telescopes is being designed to map the universe in unprecedented detail, seeking clues to dark energy's true nature. This enduring quest speaks to something fundamental about the human spirit. We are a species that looks up at the stars and asks why. It connects us to a long line of thinkers, from ancient astronomers charting constellations to scientists today decoding light from the Big Bang. Ultimately, the question of the universe's evolving shape leaves us with profound wonder and humility. We live inside a cosmos whose grandeur exceeds our wildest imaginations, a dynamic, evolving entity whose final act has not yet been written.